You're listening to Let's Talk Creation.
Well, welcome back, everybody, to another episode, our Christmas episode of Let's Talk Creation with Paul Garner and Todd Wood. I am Paul Garner.
And I am Todd Wood. And we wish you a Merry Christmas.
We do indeed. And we're really looking forward to this episode. We've got a special guest lined up for you, who we will introduce in just a few moments. But let me just begin by saying... make sure that you hit the notification bell, that you click the subscribe button to get more content from the podcast. And do remember as well to send your questions and comments in. We love to hear from you. And make sure that you like our episodes and share them with your friends. Do what you can to spread the word. It really helps us to grow the audience, and we're very grateful for all of that. Now, in our podcast so far, one of the topics that we haven't touched on really at all has been the subject of astronomy. And we know that many of our viewers and listeners are very interested in this subject. And given that neither Todd nor myself have any expertise whatsoever in astronomy or in the physical sciences, we decided that we would start to put that omission right by inviting a very special guest. And our guest today is Dr. Robert Hill. So, Robert, we are very, very glad to have you join us. Thank you so much for being here. Now, we should probably introduce Robert because, Todd, I know you've had Robert along to speak at the Smoky Mountain Creation Retreat.
Yes.
And you had a good time there.
We did.
Talking all things astronomy.
We did. I learned a lot.
That's great. Dr. Robert Hill is an associate professor in the Department of Chemistry and Physics at Bob Jones University, but he's previously taught at a number of other academic institutions. I understand, Robert, you did your doctoral research at Ball State University, and I'm going to read this because this is what your research was in. Computational modeling of the effects of star spots on the light curves of contact binary stars. Is that correct?
That sounds like a dissertation title, doesn't it?
It does, yeah.
And I don't know what that means, but it sounds very, very impressive to this non-astronomer. And Dr. Hill is a member of the American Astronomical Society and also president of the Creation Research Society. Maybe we could just begin there. Why don't you just tell our viewers and listeners a little bit about your work, particularly with the Creation Research Society? I'm sure they'd be interested to hear about that, Bob.
Certainly, the Creation Research Society is the oldest creation organization in the United States. We don't get as much public acknowledgement because of our mission. Our mission is clearly stated as to build the creation model of science. So we don't build tourist attractions.
Right.
We don't hold super duper mega colossal conferences for lay people. We don't make movies. Other creation groups do that and are very good at it. Our focus is research. As I say, research is our middle name.
True.
And so, yeah, literally. And so we do our own research. We have a research laboratory. We fund research with research grants. And we publish research, and then we hold a research conference. Word in all those is research. So the talks I give at my conference, I'm not going to be asked to speak that at a church.
Yeah. And where would people find the Creation Research Society if they wanted to find out more about the work of the society?
Oh, just creationresearch.org. Just search Creation Research Society. It should pop up pretty quick.
Okay, that's great. So go check that out, everybody. I've been a member of CRS. I can't remember when I joined. Probably sometime around the late 80s, I would imagine, 87, 88, something like that. I've been a member ever since, and do go and check out the website and consider joining if you're interested in creation research. Now, Bob, yes. Now, we wanted to invite you on because, as we said in the beginning, astronomy is one of those topics that we don't really have any expertise in. But we're both very, very interested in astronomy. I know we love to hear other people who do know about these things talk about them. And I know that our listeners do too. And I guess we can sort of begin just by sort of introducing the discipline of astronomy, because astronomy is such a vast discipline. We're effectively dealing with much, much more than 99% of the entire known universe when we're talking about the field of astronomy. And of course, it's perhaps the oldest of the sciences because, you can trace astronomical concepts way back into antiquity. So we can really only skim the surface, I think, as we sort of talk about these topics in this episode. But what we wanted to do here is just sort of give our viewers and listeners a kind of basic introduction to astronomy, to the discipline, particularly to creation astronomy, and then we can come back in future episodes and perhaps begin to look at some specific topics. So just help us here, Bob, just scope out for us the kind of boundaries of this discipline. What is it that astronomers study? What are the various branches of astronomy? How do you even begin to sort of break down the whole universe into manageable, sub-disciplines? How do you do that?
All right. So astronomy is basically the study of everything.
That's right.
Because, we start at very, very small scales, dealing with particles and particle interactions. So we're talking about particle physics and nuclear physics.
Mm-hmm.
And then we deal with very small scales, molecular physics and chemistry. You find molecules in space. Medium scales, let's talk about rocky stuff like 5-10 miles across, and then planets. The geology and geophysics is important. Then you get entire planets in the solar system. So now you're talking about gravity and celestial mechanics. You deal with stars, property of stars, how stars work. Lots and lots of physics goes into that. Big interdisciplinary physics things. Then you start dealing with galactic scales, big collections of stars, gas, and dust. Then you start dealing with clusters of galaxies. And then superclusters of galaxies. Finally, space itself. Huge range from the smallest to the biggest. Like I said, everything.
Everything.
Yeah, it is just mind-blowing. And we can't do justice to all of those sub-disciplines today. But one thing that I think, again, you might be able to help us with this, just to kind of put some of these things in context. You've talked about how astronomers study the really small stuff. Particle physics comes into, astronomy and cosmology. And then you've got the larger scales, the structure of the universe itself. Could you help us also to unpack the distance scale of the universe? Because for many of us, these distances that astronomers talk about are just incomprehensible. So can you sort of help us even to begin to try to grasp the distance scale of the universe?
Are you asking how we find the distances, or?
Well, what the distances are, I guess, first,
how
and then
big
how do we measure it?
Yeah.
How big is the universe?
Yeah.
Okay, so the methods of finding distances. The one that's easiest to think of is basically surveying techniques. And that's good to the distances within the solar system. You get beyond that, you start looking at something called parallax. Parallax is an easy concept because as the Earth goes around the sun, we get different orientations of looking at stars, and how much it looks like the star moves over the course of the year is a measure of the distance. Okay, this is easy to visualize. Now hold your thumb up. Hold your thumb up.
Got it.
Okay, now now close your right eye and look at your thumb against the background. Now open both eyes and close your left eye. Then alternate. It looks like your thumb moves. How much that moves is a measure of parallax. When it's up close, it looks like it moves a lot. You get way out there, and it looks like it moves smaller. So that method is good to, now we have satellites doing these kind of measurements. This is good to a few thousand light years. Light years of distance light travels in 1 year. The next method out is the most simple method is probably the Cepheid variables. These are variable stars. They change their brightness intrinsically. This is my annual cough. These stars will naturally get smaller and then bigger. As they do, their temperature changes and their brightness changes. And how fast that change is related to how far away they are. How fast that changes is a measure of the intrinsic brightness of that star. And so what you can do is you can see how bright that star looks to us from Earth, then use that variation in the brightness to find out how bright it actually is. And brightness falls off as the inverse square of distance.
Okay.
And that method is good for very far distances.
Huh.
Eventually, that gets hard to make measurements of. So the next method is type 1a supernovas.
Okay.
Yeah. And so the way these happen, you got a white dwarf star with a very large star near it, and they're orbiting each other. The white dwarf is siphoning gas from this other one. And so the mass of the white dwarf builds up over time. And once the mass of that white dwarf crosses the Chandrasekhar limit, there's a certain size, and it can't support itself anymore. Electron degeneracy pressure breaks. The Pauli exclusion principle quits working. And then it collapses on itself and explodes in an enormous supernova. Because of the way it happens, we know how bright it actually is. So you can see how bright it looks to us in the sky, measure. We know how bright it actually is, get the distances that way. That's how they're getting distances in extremely far galaxies.
So can I ask you why these variable stars you described, why do they get brighter and dimmer?
They are literally oscillating in size.
Oh, why? In size? Why? Why would they do that?
They have certain properties. I think what it's ended up doing is it's changing ionizations within the star itself, whether to absorb light or let it go.
Okay.
Does that in a very regular pattern.
Okay.
So in effect, if I've understood this correctly, then for things that are relatively close to us, you can use a kind of triangulation sort of principle.
Yes.
But when you're looking at things that are much further away, you essentially can't use that any longer.
We call it a distance ladder.
Yeah.
And so the parallax is good out to so far. That calibrates the Cepheid variables. The Cepheid variable is good so far out. That's used to calibrate other stuff.
Right. And what you're doing there is you're looking at the apparent brightness of an object. You know its actual brightness. So you're then looking at its apparent brightness, and then you can work out how far away it must be to have that apparent brightness in the sky. That's basically
inverse square with distance.
Yeah. So that's very helpful. So what kind of distances are we talking about? I mean, how far away are these objects? Give us some sense of what this distance scale is.
Okay, within our neighborhood, the distance from star to star is 4 light years, 6 light years, 10. The galaxy itself might be 100,000 light years across. The distance from one galaxy to another within the same cluster might be million light years. And then clusters to clusters, hundreds of million light years.
Mm-hmm.
So my car has about
it's just so difficult.
My car has about 130,000 miles on the odometer. Am I getting close to a light year?
See, since light years a light year is a distance light travels in 1 year.
Okay.
That's like 6 trillion miles, I think.
Oh, okay. So the answer is no. I'm not going to get anywhere near a light year. All right. Huh. Good to know.
Yeah.
I mean, the Earth is like 8 light minutes from the sun.
Mm-hmm. Right.
Right.
Which is weird because when you see the sun come up, that's where the sun was 8 minutes ago. The sun's already moved on. And you're just seeing it now. Very weird idea.
Yeah.
Take some time.
Yeah, it's just mind-blowing, isn't it? Yeah. So that's really helpful. So that kind of gives us some sense of, the scope of the discipline and the distances between these objects. Not that I think my mind can really grasp those distances, but at least it gives us some sort of context. The other thing that I think, before we start to sort of delve into some specifics of creation astronomy, that we perhaps ought to just talk about briefly, is what the Bible tells us about your discipline. What insights does the Bible give us concerning the origin and history of the cosmos that might act as some kind of constraints on our scientific theorizing?
Well, we're not as lucky as the geologists are. You guys have 3 or 4 chapters. Genesis 6 through 9 gives you a lot of data to work with.
Yeah.
We've got the creation week. Day 1, the heavens, the earth, and light. Day 4, the sun and the moon are directly mentioned. And then he made the stars also. The rest of you.
Oh, by the way, that happened too. Yeah.
Mm-hmm.
Yeah.
Which is an interesting thing, is we just don't have much to work with.
Yeah.
Because the purpose of these things, signs, seasons, and so forth, astronomy has typically been used for timekeeping.
Mm-hmm.
And that's an impressive thing by itself.
Mm-hmm.
Yeah.
But
yeah. So in a sense, I mean, that you could see that as a hindrance, that the Bible doesn't actually tell us very much. But on the other hand, it also perhaps gives us a great deal of freedom in terms of developing models and exploring different possibilities for explaining the data. So it's whether you're a glass half full or a glass half empty kind of guy. So that kind of brings us on then to I think, the discipline of creation astronomy itself. And from what I've read of the literature, and I'm, like I say, I have no expertise in this, but I do sort of delve into the literature a little bit, dip into it. It seems to me that there are sort of 3 broad areas of creation astronomy research. that you can probably sum up as design, origins, and age questions. And I just wonder whether we could sort of briefly explore each of those in turn, maybe highlighting some areas where perhaps creation astronomers have been able to make some progress, and some areas perhaps where there are still lots of open questions. So the first of those is the idea of design. And I think for us as creationists, we're quite used to thinking about the concept of design as it applies particularly to the biological world, to living things, to living organisms. But what can we say about the design of the physical universe itself? Is there evidence that we can point to, for example, that the cosmos is in some way designed for life? And if so, what's some of that evidence look like?
Okay, there's actually quite a bit for this. I like the privileged planet approach. Earth is designed so that intelligent life could be here and understand the rest of the cosmos.
Wow.
Usually ends up being things like Earth is just the right distance from the sun. And also, the sun is exceptionally stable. You look at other stars around the same size and mass as the sun, and they're not as stable as the sun. Some of them will throw more radiation at times out into space. The sun's exceptionally stable, as if it was chosen for this. The moon is just the right size to make eclipses possible and spectacular. No other moon in the solar system around the planet is like ours in that sense. Now, that by having it be that way, allowed us to observe the solar corona and open the door to astrophysics. The element helium was discovered in the corona by spectroscopy. Also, the early test of general relativity had to do with the way stars were able to bend light from the stars around and match general relativity quite well. Open the door for cosmology, large-scale structures. The moon itself, by being so big compared to the Earth, it gyrostabilizes the Earth's spin on its axis. Because as it spins, it's likely to start precessing. So changing that tilt's very important for seasons. That changes much. Our seasons change dramatically. The moon, by being the size it is and the distance it is, that is very stable, which certainly helps life on Earth. The moon at this size and distance produces strong tides in the oceans, which then will wash the coastlines and bring in nutrients to the coastline, making life on Earth possible. Also, there just so happens there's a large planet in just the right place in the solar system that'll deflect a lot of asteroids and comets away from the Earth. Jupiter. Also, the location of where the solar system is. We're not in a globular cluster. It would just be light all the time. You wouldn't be able to see anything else. By not being there, we have less radiation coming down, and also we can see the rest of the universe. We're in the Milky Way galaxy, and we're in between two spiral arms in just the right place, away from a lot of nearby supernovas because we're farther out, reducing the radiation coming down the Earth, and allows us to see the rest of the universe. We're not in the galactic nucleus. We've got lots of supernovas going off, very dangerous. And we can see the rest of the universe because we're not there. Things like that.
Yeah.
Also, you look at just the beauty of a lot of the cosmic stuff. There is a website, Astronomy Picture of the Day, APOD. You go there, you got these incredible pictures. People love those. They make posters of them, put on the wall. This is God's own artwork.
Yeah. That makes
So that's interesting. So
I'm just interested in the eclipse. I want to comment on the eclipse and then we can go on. Because
okay.
I've heard this argument before that, oh, hey, the moon is just the right size that we can have full eclipses. And I've always thought, well, so what? That doesn't make the Earth better for living. But that makes more sense now that you explain it that way, because it's unlocking our ability to understand what we see.
As if God wanted us to know the rest of the universe and see how great he is.
Ah, I get it. I get it. Thank you.
Yeah.
I understand a little better now.
So that's really interesting, because there are some aspects that we might point to as design features which people kind of dismiss because they say, well, if it wasn't like this, we wouldn't be here to observe it. But actually, when it comes, for example, to the eclipse situation with the moon, it didn't have to be that way. But actually, it's really, really good for us that it is.
Yeah, it's funny
because it allows us.
The evolutionists talk about this. Oh, yeah, this is a lucky accident allowed us to do this, this, and this.
Right.
Yeah, lucky accident. Real lucky.
Yeah. And as you say, there are lots of those lucky coincidences concerning sort of the solar system and where we're located and all of those kinds of things. What about more broadly this thing that I hear referred to sometimes as fine-tuning, the fine-tuning of the universe? What is that all about?
Yeah, basically it comes down to the laws of physics have just the right values to allow intelligent life.
Mm-hmm.
For example, gravity is an inverse square law with distance. The electric force is an inverse square law with distance. Well, in theoretical physics, we do this in my mechanics classes. What if that exponent was something other than 2? What if it was 2.0001 or 1.99999? If it is something other than 2, orbits become unstable.
Huh.
For gravity, the solar system would slowly fall apart. Electrons would do weird things, and atoms and molecules would be unstable. If you want to have life, that needs to be a 2. God chose wisely.
Yeah.
I guess so.
Also with that, you look at the values of the fundamental physical constants. The universal gravitation constant, and then electric permittivity of free space, magnetic permeability of free space, the Boltzmann constant, the electron mass, all these kinds of things. It turns out, if you change any one of those by just a little bit, it's like the universe destroys itself. Or else things happen and you might get bacteria, but that's it. Nothing else could live. It's like these things were chosen to allow intelligent life to exist.
Yeah, that's amazing.
That's fascinating.
God know what he's doing.
Yeah.
Yes, he did. And I sometimes hear this idea about fine-tuning sort of discussed in the context of the anthropic principle. And I understand there are different forms of the anthropic principle, but what could you tell us about that? Could you just sort of unpack what the anthropic principle is and perhaps how it differs from a creationist type of design argument?
I think the anthropic principle is more or less, we can exist because these other things are true. And I think it's the broad idea where creationists approach it like, well, God was certainly a genius picking these numbers, wasn't he?
Yeah, exactly.
We have someone to give credit to.
Yeah.
And admire and worship.
Yeah.
Yeah.
But it's interesting that there is this thing called the anthropic principle that suggests in some way that even non-believers recognize that there is something anthropic, something man-focused about the creation itself, which is really, really interesting that they recognize that, even if they can't account for it in the way that we can as creationists.
Well, that's one reason they have like the many worlds interpretation of quantum mechanics.
Mm-hmm.
All these other things really did happen somewhere, and nothing happened. We just happened to be the one that worked. So all of them were tried.
Right.
But we're the one that worked.
Yeah.
Never mind,
well,
that's not really science. It's pure speculation.
Right. Yeah, that's very helpful. So that's design. And then the second kind of big area I see in creation astronomy concerns origins, obviously. How would you say that creationist astronomers approach the origins questions differently to non-creationists?
Well, this is where your worldview dictates a lot of things. The worldview you hold will affect how you interpret data.
Mm-hmm.
And so, if you're already convinced of like an evolutionary long age time span, you naturally interpret everything through that filter. As creationists, we're allowed to consider options they wouldn't consider.
So I guess the big difference is that a non-creationist is in effect tied to a naturalistic type of explanation, whereas we can perhaps explore non-naturalistic explanations for phenomena and other kinds of explanations outside of the mainstream, and that opens up some research possibilities for us. I guess what most people associate with a kind of secular view of astronomy is the Big Bang model, in terms of the origin of the universe itself. Just tell us a bit about the Big Bang model, and what work have creationists done to try to develop alternatives to the standard Big Bang cosmology?
That could take a couple of days,
True. Is a big question.
All right. The rationale for the Big Bang cosmology starts with the observation that galaxies are redshifted in their spectrum, implying they're going away from us. Measured thousands of times, and the relationship between how fast moving and the distance they are from us is pretty linear. So you project backwards when everything was closer together. There was a time in the past where everything was on top of each other. That would be the beginning of the Big Bang.
Yeah.
Okay.
That's the observational what drove this. Since then, you have to explain this, you have to fold in general relativity, particle physics, all kinds of other stuff. That's like the quick, dirty. This is why they think this. And then, as far as creationists looking at it, well, alternatives, we haven't done enough. The big problem we always have is there's not enough astronomers who are creationists who have credentials in the field. Biologists and geologists are in pretty good shape. You have enough people, you can explore things, bad ideas around. The number of creationists with credentials in astronomy, I could count on my hands. Too many times we've got well-meaning people whose degrees might be in chemistry or engineering, shooting their mouths off with something they don't understand. They never had astrophysics in their life in class.
Yeah.
They mean well.
Yeah.
And they're smart. But they don't have the background to evaluate things well.
Yeah.
I like talking to you because it reminds me how utterly ignorant I am of your field. I read some of these books and articles and I skim them. I can't really understand them. And I can sort of make some interesting, outside observations of sort of philosophical issues and things like that, but I have no concept of any of the physics behind it. So it's good to talk to someone like this to remind us to be humble about about the origin of the cosmos.
Now, attempts have been made. The first real attempt was D. Russell Humphreys with his white hole cosmology. He's since moved on from that, but it was pivotal in changing the way we started thinking about things. This opened the door for general relativity into the creation movement. For some reason, we thought general relativity was kind of like natural selection and mutation for neo-Darwinism or something. But once that opened the door, and there's been other attempts made, but there's absolutely no consensus right now. We've had suggestions being made. One guy presents a model, another guy presents a model. We don't have enough people who could then debate, like, that's a problem here, you need to tweak that, there's a problem there, you need to tweak that. Oh, that's good. Yeah, like individual personalities, everybody wants to be the next Einstein.
And I think that
model.
Yeah.
Okay, I think there's a challenge there, isn't there? That we need young creationists who perhaps have skills in physics and so on to maybe specialize in areas like cosmology and astrophysics, so they can contribute to this research effort, because there is so much work to be done and so many opportunities that there would be to make a real contribution in creationism for those who are so inclined. So there's a challenge for young students to consider whether that's a field they could go into and contribute in. There's all kinds of other aspects of this origins question that we could talk about. I mean, besides the Big Bang, because we're only talking there about we're talking about the origin of the universe as a whole, but there's all kinds of things. There's the evolution of large-scale structure in the cosmos, and there's evolution of galaxies and life cycles of stars and the origin of planetary systems. And we don't have time in this episode to kind of get into the weeds on all of those, but there's such a huge amount of work to be done in all these areas. I think I'm right in saying.
Mm-hmm. You're correct.
Yeah. And then the third aspect of creation astronomy research that we should briefly touch on concerns age questions. I think it's fair to say that most creationists think that not only the Earth and life on the Earth are young, but also the cosmos itself is young. In contrast, obviously, to conventional astronomy models, where the universe is about 13.8 billion years old, I think, and the solar system about 4.6 billion years old. So there's a huge difference here in terms of how we think about the age of the objects that we're seeing. What work has been done by creationists to look at age indicators that might point to a young cosmos? Do you have some examples of work that's been done there?
Okay. One of them is recession of the moon from the Earth.
Mm-hmm.
The moon is slowly getting farther away from the Earth, in order like a centimeter or so a year. And we can measure that from retroreflectors left on the moon by the Apollo missions. Literally bounce a laser from Earth off the moon and back and time it. So that we have very precise measurements of that. So, conservation of angular momentum involved here. The moon is tidally locked to the Earth. It can't change its rotation. The Earth is slowing on its axis. The spin is slowing. We can measure that with atomic clocks. And that slowing is primarily due to tidal friction of the oceans on the ocean floor. Earth is slowing. That means it must transfer angular momentum to the moon. And the moon speeds up its orbit, so it slowly gets farther and farther away. So backwards in time, the moon must have been closer. The closest the moon could have ever been is the Roche limit for the Earth. The Roche limit is the distance from the Earth at which an object cannot be held together gravitationally. Outside that, it's fine, enormous tides. Inside that, gravity can't hold the object together. So take it from the Roche limit out to its current distance, that's like 1.4, 1.6 billion years.
Oh.
That's a lot. But Earth-Moon system is supposed to be like 4.6 billion years. So something's going on there. The usual evolution attempts, well, the moment of inertia of the Earth changed over time. You need more. Yeah, that needs more work. Another one that's very interesting is the faint young sun paradox. Okay, in the standard model for the solar system, the early sun should have been faint. But on the same time scale, life should have evolved on Earth and been thriving. You need more heat and light from the sun for this, yet the early sun was faint. So they start arguing, well, maybe there's more carbon dioxide in the atmosphere, the greenhouse effect. That's a problem. Maybe it's not that. One of Jupiter's moons, Io, is the most volcanically active body in the solar system. Every time you send a space probe by, there's a couple of massive volcanoes going off. Well, it's so far away from the sun, shouldn't it have cooled down by now? Well, the usual explanation is Io is in a 421 resonance with other moons, Ganymede and Europa, other moons of Jupiter, and then it's like for every time Europa goes around Jupiter, Io goes around twice. It's a resonance. Every time, like I think it's Ganymede goes around once, Io goes around 4 times. That tends to make the orbit more elliptical. And so, because of that, Io is constantly being stretched and then let go, stretched and then let go. That heats at tidal heating. You get a similar effect if you take a rubber ball and squeeze it a bunch. Or you can really see how the mechanical work on an object is a heating effect. Take a paper clip, do this with it until it breaks. Mm-hmm. You put your finger right where it broke. That's downright hot.
Yeah.
So they're thinking something like that's going on with Io. That sounds like a good explanation. However, when you actually look at the numbers aren't matching up. So how much heat it's giving off, it's still too warm for that, implying young. Enceladus and Triton are moons, Saturn, I believe, and they have cryovolcanism. Instead of lava, we're talking about ice volcanoes.
What are they spewing? Water or ice?
Ices.
Okay.
Like slush.
Okay.
It's so cold. You have like just slush things thrown out. Well, Io is weird because it's sulfur, not rock. And so I think that's tidal heating, and you run into the same problem. A favorite for a long time is the idea of short period comets. A comet is every time it goes around the sun, loses some of its mass, because the sun heats it up, making the tail. Ice sublimates and gets pushed out, dust goes out. Well, a comet can go around the sun maybe 100, 200 times, something like that. But it's losing mass every time. Now, a short period comet, one has a period, less than 100, 200 years. Who's making the definition? Well, if the solar system is 4.6 billion years old, why do we still have short period comets? They should have burned out by now. Now, evolutionists aren't dumb. We have to get away from that idea. And so, I remember when I was in grad school, I asked one of my professors, so, The explanation is there's a comet bank way out there called the Oort cloud, named after Jan Oort who proposed it. And these really long period comets, 100,000 years for periods. Every now and then, when they get in close to the sun, Jupiter or something perturbs the orbit, and now it's a short period comet. Somewhere in grad school in the 80s, I think, I asked one of my professors, so what really is the best evidence for the existence of the Oort cloud? And he's like, yeah, that's a good question. I suppose the best evidence for the existence of the Oort cloud is we still have a short period comets.
Right.
Okay.
Now, we do have evidence that some comets are long enough period. They go out in that range, but you actually need something in orbit, long period orbit around the sun. They haven't seen that yet. It's really hypothetical.
So these arguments you're sharing with us, these are what I would call little hints and teases, right? They're not getting us to 6,000 years ago.
Right.
They're just telling us there's something wrong with the way we're thinking about the universe as it appears at first glance. Is that right?
That's basically it.
Yeah. So if you sort of at first glance look at it and you sort of make some really simple assumptions, you come away with, oh, this must be billions of years old. And then you start looking more closely and you realize, oh, well, that's not going to work for
Something's
this.
up.
Yeah, something's funny going on here. Yeah. Okay. That's good to know.
Yeah. That's very helpful. So we do have these sort of clues that might cause us to start to question the conventional chronology. But as creationists, we also face some quite thorny problems of our own, I think. And the one, of course, that everybody talks about is the problem of the travel time of starlight. And I know that's a huge issue. We're not going to solve that one in the last few minutes of this episode. No. But do you think within the creation model that there's the prospect of being able to address some of those types of questions through the research that's being done?
Well, to be honest, this may be a mystery until Jesus returns.
Okay.
However, general relativity may have some possibilities for us.
Yeah.
Like Humphrey's white hole cosmology started the development of these ideas, but there's no consensus. If the Earth is, say, near the middle of the universe, which kind of makes sense given we're the center of God's attention, then if that's the case, there's something called gravitational time dilation, which has been measured. Time can flow at different rates depending on the strength of the gravity field.
Sure.
GPS satellites must take that into account. Otherwise, they don't work. So it's conceivable time could go incredibly slow where we are, but out in some galaxy might be super fast. And so that might solve it. There's other things. And it's not just a 6,000 years issue. The purpose of stars for signs and seasons, which means Adam, on like day 8, could look up in the sky and see them.
Yeah.
Yeah.
Some of this, well, is creation week, God was doing miraculous stuff. We're never going to explain that.
Yeah. Yeah. That's very helpful. So, yeah, we've looked at those three sort of big areas: design and origin and age. And it seems to me, listening to what you've had to tell us, there are loads and loads of unresolved questions. There is enormous scope for creationists to do more work in all of these areas. And I think in many ways,
need a few hundred
cosmology cosmology is one of the most underdeveloped areas of the creation model. And we desperately need more.
Trying now. Before it's just like, well, God did it.
Yeah.
Mm.
Yeah.
Okay, God
Yeah.
gets an A, but
Yeah. But we desperately need more workers, don't we? We need more people who are trained in these disciplines to help us. So that's very helpful. We're fast running out of time with this episode, and I feel like we've kind of raced through so many topics, and we're going to have to come back to many of these in future episodes and look at them in more detail. But we did want to close out this episode because this is our Christmas episode. And here we are talking to an astronomer, and we just could not resist the opportunity to ask you about the Star of Bethlehem.
Now, what was it?
What was the Star of Bethlehem? So we've got this description in the Gospel of Matthew in chapter 2, in the nativity account there, of this star that directs the wise men to the place where, Jesus is. And of course, there have been loads of attempts over the years to sort of explain the star and to give it some kind of scientific explanation. And I just wonder whether you could sort of help us. What are some of those scientific explanations, and do they work? What are the merits or demerits of these ideas?
okay. One attempt was saying it's a comet. Long tail. There's even a Christmas Carol with that. Tail as big as a kite or whatever it is in that song. Mm-hmm. Comets definitely would not work, because comets, forever in ancient times, they were seen as omens of something very bad. There was a comet in the sky. Julius Caesar was assassinated. There was a comet in the sky in 1066. The Battle of Hastings in Britain lost. So forever, comets were seen as something bad. So no one would associate that. Also, no one else saw this thing. That ends up being a significant thing. Remember, the wise men came to Jerusalem. We saw his star on the east, and no one there knew anything about it. And so comet just doesn't work. Some suggest maybe a shooting star, a meteor. Those could point. Oh, yeah, but they don't last very long. And if you had something lasting that long, it would have been written down by somebody. This is unusual. People such a nova or a supernova, too short in duration. No one else saw this. Because you have to remember, even today, we don't look at the sky much. Back then, especially in those areas, Jerusalem used a lunar calendar. The month was determined by the phase of the moon. And so, the beginning of the month is new moons. They had people watching the sky. The 15th of the month is the full moon. Notice most of the festivals are like on the 15th of the month. And so people were looking at the sky. Unusual things would have been noted. Also, this idea that in looking at planets, because they move around the sky, is what they're called planets. Planet means wanderer. So planets are stars that move around from night to night. And so it's been suggested there are like 3 planets got really close together, and that was the star. Well, you could look at the program and see how close they would have been. They never would have been close enough from the sky to be seen as a star. It would have always been 3.
And you would think they would know, right? I mean, because these guys know where the planets are, they would know. Oh, look, Jupiter and Mars and Venus are all together. They would know that that's not a star, right?
Yeah, they know there's 3.
Yeah.
Well, they were called. Planets are considered wandering stars.
Yeah.
Any light in the sky was a star.
Yes.
Planets moved around from night to night, so they were special. And so that just doesn't really work. None of them really match up with an account in the Nativity. I would go with something supernatural. It was a time for supernatural stuff.
Yeah, it sure was.
Yeah.
And the only account we have is in Matthew. See, when when the Magi got to Jerusalem, notice they didn't go straight to Bethlehem. They went to Jerusalem. Something told them something big was happening. Naturally, go to the capital, Jerusalem. No one there knew what was going on. Then they saw the star again, and it was that led them to Bethlehem. This seems something very special. They're the only ones that really saw or understood what they were seeing.
Yeah.
And of course, the important thing was the Magi got there when they did. Because right after the Magi got there, what did Herod decide to do?
Yeah, he decides to kill
all the babies.
Yeah.
So Joseph and Mary and the baby Jesus had to leave right now. Well, they weren't that wealthy, so they had to take off and just leave whatever they had. But after the Magi were there, now they've got gold, frankincense, and myrrh. 3 very compact, very, very expensive things. So Joseph could have easily bought his way into a caravan to Egypt. Hey, here's a bag of gold. Can you let me in?
Yeah. Okay, yeah, sure.
Yeah.
Yeah.
Yeah, that's very interesting. As I've thought about the Star of Bethlehem, I can't help but remember the fact that the people of God in the Old Testament were led through the wilderness by a pillar of cloud by day and a pillar of fire by night, and
miracle
that
stuff.
God often guides his people, by supernatural lights. And the fact that it stood over where the child was. Yeah. It's very hard to imagine an astronomical object pinpointing a particular house in a particular place. But
because it'd have to be very, very close to the planet, right, to be able to say, oh no, it's not right overhead yet. You'd wander from house to house and realize, oh, it's this place. This is it. That's very low altitude. You couldn't do that with an actual star out in the hinterlands of the universe, because they wouldn't get that specific. I've always thought there's no way this is a star as we think of it. This is too weird.
Yeah. Well, that's fascinating. We need to start to wind the episode up, I'm afraid. But this has been a really interesting discussion, and I definitely hope we can come back and explore some of these topics in more detail in future episodes.
Oh, I'd love to.
So, thank you very much for your time. We've really appreciated having you here as a guest.
Me.
It's our pleasure. Now, we don't know, I think, necessarily what's coming up next, but
always a surprise.
There's a bit of a break because this is our last episode before the Christmas holidays. Do remember to check out all of our streaming platforms and our show notes and all of that stuff on our website, which is coursesci.org/podcast. And of course, if you have comments and questions, we love to hear from you. You can email us at podcast@coursesci.org, or you can leave comments on our YouTube videos. As we said at the beginning of the episode, don't forget to subscribe to our channel. Hit the notification bell so that you get notices of future episodes. Like, share, leave a positive review. All of that helps. And Todd, this is the Christmas season, and it's a time for giving, and we need to just talk about donations from viewers and listeners. So
we do.
You've been doing some number crunching, we've mentioned in previous episodes, and we've worked out that it costs about $600 or about £500 here in the UK per episode to keep the podcast coming. So if people would like to help us to cover the costs of producing the podcast, and of course it's subsidized by the ministries that we both work for, how do people go about doing that? If they want to give to the work of Core Academy, Todd, tell us how people can do that?
Yeah, we would ask you to check out coresci.org/donate. coresci.org/donate. That is a place where you will find links to all of our giving options, including our mailing address where you can send your checks, or you can give us money online through PayPal, or you can sign up for become a monthly donor by PayPal. And we would appreciate all of that. If you want to specifically discuss having your idea on the podcast and supporting a full episode, sponsoring a full episode for $600, feel free. We will be happy to talk to you about whatever ideas you have. And we would be happy to include your work or your ministry as part of the sponsorship package as well. So that's a possibility for those listeners who are interested in that kind of outreach as well. So we can talk about that. Paul, where can we give to the podcast in the UK?
Yeah, well, if people want to visit our website, biblicalcreationtrust.org, there is a donate button on the homepage, and that will take you to a web page that tells you all of the options for giving, how you can give regularly, how you can give a one-off donation. There's a PayPal facility, particularly if you're outside the UK. That's probably the most efficient way to give to Biblical Creation Trust. And we are very grateful for all those who give and help to support the work that we're doing and help to keep the podcast happening. Well, that's the end of this episode. It's been a fun episode, and we'll see you in a couple of weeks' time after Christmas. But we should end by wishing you all a very, very happy Christmas.
Merry Christmas, everybody.
And we'll see you in a couple of weeks. Happy Christmas.
Thanks for listening to this week's episode of Let's Talk Creation. If you have questions, send them to podcast@coresci.org. That's podcast@coresci.org. And be sure to let your friends know about Let's Talk Creation. And check us out on social media. Thank you.